Okay. All right. Ready? Welcome to EE123 Lecture 3. Woo! Okay. Frank, I didn't have a chance to read your announcements, but any announcements?
Homework due Friday, lab due Thursday, office hours are posted on.
Okay, lab due Thursday, homework due Friday, and office hours are all posted on the class website. Hey! I'm talking now. All right. So a couple of things. You should start reading the book. Read chapter 2, 2.0 to 2.9. The book has very nice descriptions of the material. It's okay to use second edition. Class webcast is in B courses, but also linked from the website. But it takes me a couple of days to update the link. So if you're eager to go and rewatch, get a rerun of this show, then go ahead and go to the B courses. Office hours are posted online. I'm going to have 3 types of office hours. So Wednesday, 4 to 5 p.m., that's EE123 priority. From 5 to 6 p.m., I'm going to be in the ham shack. Anybody who wants to operate a radio and talk about radios, I'm going to be there. From Thursday, 2 to 3 p.m., it's going to be EE223. It's another class that I teach, class on MRI, which is by far the most amazing imaging modality. If it's empty, then I'm happy to answer your questions, but the priority is going to be for the particular class. $2 for every typo errors in my slides, so pay attention. And people have made quite good income out of this. Ask your friends that took this class whether they got compensation or not, and let me argue that some of them got even more than they should have gotten. So anyway. Ham radio lecture, just a reminder, Wednesday 6:30 to 8:30 in Corey 521. There was a cap for some reason for 20 people for this. We removed the cap, so now it's open. If you haven't registered and you want to, so please go ahead. Okay, any questions before we start? You ready? Yeah. So check off of the lab needs to be done before Thursday. Is that correct? What does it mean do?
Well, there's a B courses assignment. We have to submit it there.
Yeah.
We're still figuring out.
Okay. So for lab 0 is just going to be okay. So for lab 0, submit it on B courses. Okay. We'll figure out the administration for actually doing the checkoff in the future. We have a meeting about that today. Okay, so any more questions before we start talking about some discrete time systems and discrete time Fourier transforms that you've already should have known? All that. Okay, so all you guys that probably you should know this, so you're going to be super bored in this lecture. Okay, and if you're not super bored, that's going to be a problem. Okay, remember that. So you need to kind of read up on the material if you're not super bored. Okay, so try to get super bored here. Okay, so discrete time systems. We talked about what is a discrete time system. A discrete time system is you put a discrete signal in, and you get a discrete signal out. Okay, now it could be that there's something continuous happening here in the middle, but in a discrete time system that you're gonna see, like why would you even have a continuous time, in the middle? Well, there might be a good reason to do so. When we get there, we'll get there, and try to kind of relate what discrete time systems actually correspond to continuous time. But for now on, let's just assume that everything is done discretely. We talk about properties. Remember properties of these systems? Causality, memoryless, superposition. Just Sum and all in one. Yeah, linearity. Time invariance. What kind of stability? Bibo. We didn't talk about that. I didn't even actually say Bibo, but actually you're right. Bibo stability. And what is Bibo stability? Bounded. That's great. You see, I don't need even to teach this class today. Okay, Bibo stability is bounded input, bounded output. So discrete time LTI system are characterized by this wonderful thing. So if you have an LTI, linear time invariant, or linear shift invariant, why would I say shift? Could be space. Doesn't have to be time. So don't focus yourself on time. A lot of people deal with space. Space is important. Okay. So linear time invariant system are a class of systems that are very, very powerful and very important. And there's one thing about those systems that makes them amazing to analyze, and that's the impulse response. And the impulse response of a LTI system, if you think about it, is kind of like the DNA of it. The amazing thing and the useful thing about this is that once you know what is the response of an LTI system to an impulse, you know everything you need to know about that system. So what is an impulse response? Let me just give you an example. Oh, I set it up and then it went away. Okay. So give me one minute here. QR code. There you go. This works. Great. Connected. Where you are? This is my phone you're seeing now. There you go. So what you're seeing now is the accelerometer on my phone. It's pretty cool, huh? All right. Ready to measure an impulse response? That was not impressive, huh? All right, again. It's kind of a poor one. Okay, that's better. Okay, so what you see here is a response of that system to some sort of an impulse. Is this an LTI system? Is it? Depends. Okay? Generally, no, because if I move over here or I move over here or so on and so forth, that's not going to be the same system, right? It's not going to be the same system. What if I bang it so hard? What's going to happen to the accelerometer? Completely saturate, right? So saturate, then it's nonlinear, okay? So if I add more and more, like if I just bam, 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 yeah, saturate's nonlinear anymore. But if I do make small hits in the same spot, well, then it's approximately linear time invariant. And in that sense, if I want to create a certain signal over here, I can maybe characterize what the impulse response should look like. And then based on this impulse response, I can come up with certain vibrations that will try to generate whatever happens. Actually, in some way, whatever I do now, I can predict, by knowing the impulse response, I can actually predict what is the outcome going to be. Okay? So that is really, really powerful. Now you have to understand, this is not linear time invariant, but it could be, right? Depending if you're doing small signals or large signals, you're moving in space and so on and so forth. Things can change over the room. Okay? Usually I bring boots for this class. I forgot to bring boots. Okay, so an LTI system, you put an you put an impulse, you get h of n. And so it is completely characterized by this impulse response, and the result is a discrete convolution, basically with the input and the impulse response. And if you actually think what is a discrete convolution, it's really just a weighted sum of delayed impulse responses. Okay? This is all what it is, just the weighted sum of delayed, amplified, so delayed and weighted impulse responses. Okay? That is all what it is. Okay? So this is quite a nice property. Now we mentioned about LTI system. What is Bibo stability? So Bibo, so there's the rule for Bibo stability is that if and only if the impulse response is absolutely summable, that means that if you sum the absolute value, it is going to be bounded, then you're going to get guaranteed that if you put a bounded input, you're going to get a bounded output for LTI systems. The proof for this is actually quite simple. Okay, what you're going to do is you're going to write y of n, which is the output, take the absolute value of that. That equals to the convolution of the impulse response with the signal that you're going to put in. Triangle equality, you get effectively that this is less than the absolute value of the impulse response and the absolute value of the input. And we know that this is going to be bounded, right? We're going to put a bounded input. Then this is less than b times x times the sum of absolute values of the impulse responses, of the impulse response. So if this is bounded, then the whole thing has to be bounded. Now this is one way of the proof, but of course you have to prove the other way. And the other way, that if you know that this actually is not bounded, is there an x of n that is bounded that will give an unbounded y? Does this make sense? If you know that this is not bounded, is there still an x that is bounded that will give an unbounded y? Okay? That's the only if. And the way to prove it is also quite simple. What we're going to do is we're going to just try to find an example for which an input that is bounded will result in an output that is not bounded. Okay? So an example is choosing the sign of the signum function of the impulse response. If you look at the signum function of the impulse response, is this bounded? What is the values of a signum function? 1 or minus 1, right? So it is bounded. Okay? All right. So if it's bounded, then we can perform the convolution between the signum and the signum of the impulse response and the impulse response. So you get the following relationship. Now, if you just evaluate that convolution at y equals 0, okay, we're just going to evaluate at one point. Okay? At y equals 0, n equals 0, so you got hk multiplied by x minus k. Okay? Now we can write this down as this function. Okay? So you've got h of k times h of k divided by the absolute value of h of k. All right? I'll let you digest it for a second. If you substitute this over here, we're going to evaluate that convolution at n equals 0, exactly when they're matched. Then you've got h of k squared divided by the absolute value of h of k, which means that this is actually the absolute value of h of k, right? Something squared divided by absolute value of the same thing gives you the absolute value. Then you sum over that. Now we know that this goes to infinity. So then you get infinity. Means that we put an unbounded input and we got a, we put a bounded input and we got an unbounded output, right? So, QED, questions? All right, we proved both ways. All right, moving on. The one thing that, so this is from all this material from last lecture that I didn't have a chance to go through. Today we're going to go over the discrete time Fourier transform. But just to give you kind of like a context of what we're actually going to do. So in the next few lectures, we're going to learn new tools. Okay? Transforms are tools that you can use both to analyze and synthesize things. Okay? So we're going to build a set of tools. We're going to talk about the DTFT, we're going to talk about the DFT, the Z transform, we're going to talk about the wavelet transform, and so on and so forth. And all of these are tools to analyze signals. Okay? They enable us to look, and we're going to also look at the discrete, the time. Help me here, Frank. The time Fourier transform. Discrete. Is that discrete? When you shift over time, spectrograms. How do you call this? Short time. Thank you. Short time. The short time Fourier transform. So all these are tools, okay, that we're going to learn how to analyze signals. Okay, so we're going to start with the discrete time Fourier transform, and the discrete time Fourier transform is very similar to the Fourier transform. Only it has sums. Why does it have sums? Because it deals with discrete signals. So x e to the j omega equals to the sum of k minus infinity to infinity of x k e minus j omega k. Okay? And we're going to sum over k, so we're going to end up with a function of omega. So we start with something discrete, we end up with something continuous. That's interesting. Think about that. You have something discrete, and the transform gives you something that is continuous. At the same time, the inverse Fourier transform, or the inverse discrete time Fourier transform, is the integral over the period of pi. And why is it of 2 pi? Why is that would be a period of 2 pi? Because, as it turns out, the discrete time Fourier transform is periodic and has a period of 2 pi, just by the way it is represented. So it's the integral from minus pi to pi of x e to j omega e. And here, the only difference is that we're going to use a plus j as opposed to a minus j. But now what's interesting is that now the result is a signal which is discrete. Okay? So as it turns out, frequencies are actually continuous, but the signal is actually discrete. So this is why we're going to represent it that way. And you're going to see that maybe if you want to capture the entire information, you probably don't need to have this full representation in order just to capture that information. So maybe we can sample the discrete time Fourier transform and still be able to have all that information. And that's going to lead us to the DFT. Okay? But the discrete time Fourier transform is actually a continuous representation. An alternative way of writing this is as a function of f as opposed to as a function of omega. So you can write it that way as well, so 2 pi fk instead of using the omega. There is somewhat an advantage to this over this one or vice versa. And what I like about this is that it's pretty much symmetric. There's no constants. Okay? There's no, here you have to remember, do I have to divide by 2 pi or not divide by 2 pi? Here, it's the same. So there's nice symmetry about this. But this is what's in the book, so we're going to use this representation. Okay? Sometimes, though, you can see that in some other places as well. Okay? So let's look at some examples of the discrete time Fourier transform. For example, what is the DTFT of a window function of size 2n plus 1? Okay? So it's a window function that has a size of 2n plus 1. Okay? How do you compute it? How do you compute it? How do you compute it? What? Yeah, just use the formula. Okay. So let's just write it up. Okay. Just write it up. So you start summing from minus infinity to infinity, but that function is only defined from minus n to n. Okay. It's only defined from n to n. So it's the sum of k minus n to n e minus j omega k, right? Because this is actually a constant before it. Okay. So just summing all over ones between minus n and n. Well, that's great. I want to get into a nicer shape, a nicer form, because this is not really a closed form. So what I'm going to do is I'm going to take a factor of e minus j omega n out. And so now I've got a sum that goes from 1 all the way to 2n, okay, of these complex exponentials. Okay, make sense? I haven't really done anything. I'm just kind of massaging this equation up. Now, the reason to do this, what does it look like? What? A geometric sum, a finite geometric sum. And if you recall that a finite geometric sum has a nice equation solution. And so in this case, this p is really e to the j omega. And if we substitute this m by 2n, you got yourself the result. Okay. So now, let's look at what we have. So e to the minus j da, 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 da. I'm going to use the geometric sum, and I'm going to get this. Okay. Well, that's great. I have this plus 1 over here. I don't like it. I don't like this plus 1. I'm going to take it out. Are you ready? Yep, let's take it out. We took it out. Now it's out. That's great. I also didn't like this one, so I multiply this by this, I multiply this by this, and I got this. Okay? So multiply this by this by this, and I had to take it out. So this is the result of multiplying this by this and ignoring this one. That's great. Okay, so we've got this expression. I don't like it too. I want something to look like something I like it. So I'm going to multiply both sides by e minus j omega over 2. Now you'd ask, like, why do you want to do that? Well, the answer will be symmetry. I like symmetry. Let's put symmetry into this. So once you multiply by these constants, by these terms, now I've got something that looks interesting. I got some e minus j omega minus e to the plus j omega something. Okay? Same expression here, same expression here. At the bottom, e minus j omega over 2, e minus e j omega over 2. Well, that's great, because if you have something that looks like this, everybody here should know that this is really a sinusoid of what's on the up, and this is a sinusoid of what's on the bottom. And you got yourself the following expression. Do you know what this expression is? What? Ah, that hurt, Frank. Right? How can it be a sinc? I thought sinc is like sine something over sine x over x.
It's a relative of a sinc. Because it's periodic.
That's right. That's absolutely the difference. It is a periodic sinc. Okay? So now, when somebody tells you, what is the Fourier transform of a rect function? You've taken EE123. You can have a smart comments like, are you talking about a discrete rect function, or are you talking about a continuous rect function? Because they're not exactly the same. One will give us an actual sinc. The other one will give us a periodic sinc. Okay? Does this make sense? Same, but different. And that difference is sometimes a big deal. Okay? Because it looks like a sinc, but it's not really a sinc. Okay? It is a periodic sinc, or Dirichlet function. Okay? Dirichlet kernel. And I'm sure this can be pronounced in many various other ways that sound similar to what I just said about Dirichlet, but probably expressed slightly differently. And I don't know, just an anecdote. So do you know that Siri can be taught to actually pronounce things correctly? I just only figured out the other way. I collaborate with this pediatric radiologist, Dr. Shreya Vasanawala. And like, this is really hard for Siri to pronounce. So now she's doing a pretty good job. You can train it. All right, just an anecdote. That's a story. Okay, so this is how it looks. This is what's called a periodic sync, and it looks the following way. Okay, it kind of looks like a sync, but it ends like there's. From now on, it's just going to be the same way. It's going to be periodic, right? So it's not a sync, because syncs go to infinity. Okay, remember that. But it's still a beautiful shape, right? It's gorgeous. All right, so. How do you know what the value at omega equals 0? Just simply from L'Hopital rule. Okay. It is also, by the way, the sum of x of n. Okay. Right, the DC component, effectively. Okay. So if you just think of what is the evaluation, you'll see that that's going to be its value. Okay. If you just evaluate itself. That's going to be the sum of x of n. Because that's, when omega equals 0, the coefficients are really 1s. Okay? All right. It also has one, in that case, it has two zero crossing. One of them happens at pi over, so this one, pi over n plus half. Okay? And then one last thing I want to ask you is the value here is 1. At pi. And why is that? How do you immediately know that the value at pi is 1? The what? Odd number of non-negative terms. And how many? Right, there's 2n plus 1 values. And what is the frequency omega equal pi? Right? The highest frequency, plus minus 1. Right? And you sum over them. So you multiply plus minus 1 over your 1s. Now you sum plus minus 1s. Plus 1, cancel. Plus 1, cancel. Plus 1, cancel. Plus 1, negative 1, cancel. Cancel, cancel. But it's an odd number. You have to end with a 1. That's going to have implications when we talk about filters. Because if you have an odd number of odd filter, you might end up with some value, and you're going to still pass some frequencies. Like, there's not going to be a null at pi, right? It's going to be attenuated, but there's not going to be a null there. Okay? Remember that. Odd, even. Now you have to think about this. Continuous time, who cares? Discrete time. You have to be careful. There's some things that you cannot do with an even number filter, for example. Okay? Okay, so let's talk about some properties. DTFT is periodic because if we add 2 pi to our omega, it's exactly the same. So it has a period of 2 pi. Has another nice property. One of them is the conjugate symmetry. And this is interesting just from a information point of view. If you think about this, so what is conjugate symmetry? It means that the conjugate, basically what it means, that one side of the Fourier transform is exactly the same as the other side, mirror of it, with just a conjugate value. That means that you only need to know one side of the Fourier transform if your signal is real. If x is real, then you have this conjugate symmetry. Now, the beauty about this from an information point of view is that when x is real, that means that you have reduced degrees of freedom, right? Like your space is now only on the reals, it's not on the complex plane. Your dimensionality is low. In that sense, if you look at the Fourier transform, it should have some redundancy. Right? Because you're not using the entire space. Okay? You're only using the reals. If you're using complex, now everything fills up. Okay? So that kind of makes sense from an information point of view. Okay. So conjugate symmetry, the real of the flipped version is the same as the real of the original version of the Fourier transform. And if you look at the flipped version in the imaginary part, then it's going to be conjugate, so negative to it. Okay? That's what it means. Now, this is actually a big deal. It's a big deal for example, for one of the most amazing fields, which is the field of MR, but also communication. I mean, yeah, not so big, but I guess quite more big in terms of just capacity. But it is a big deal. And the reason it's a big deal is in MRI, we're actually looking at, spin density inside the body. Spin density should be like a real valued type of information. It turns out it's not really, but it's kind of real. So your image should be somewhat real. That means that the Fourier transform should be conjugate symmetric. If we acquire data in the frequency domain, and we collect data one line at a time, so it takes us time to collect everything. If we knew that the signal is real, we can just stop in the middle. Stop in the middle and complete that part based on the conjugate symmetry of this. And this is called half Fourier imaging. Implemented in every scanner in the world. Basically doing this. Now the thing is, it's not really real. It's just a little bit real. There is some phase. And so what they often do is acquire slightly more in order to be able to estimate low frequency phase and compensate for that fact. But just remember that. Now the other way that this appears is in single sideband modulation. Now if you look at voice signals, for example, our voice represent pressure, right? Air pressure. It is a real component. Like if I record my voice, it's I'm not going to record complex values, right? I'm going to record real values of that pressure versus time. Hence, its spectrum is conjugate symmetric, right? Now, if I want to send this or I want to transmit this, often what people will do is modulate that baseband signal. So my voice would be baseband because it's close to DC. That's called baseband. And it's going to be modulated to a higher frequency. One of the ways to modulate is amplitude modulation. And in amplitude modulation, we take the signal and we multiply by some cosine at some frequency. Okay? And then that will be modulated. Now, this is all discrete right now. I'm showing it to you. But, of course, it can be done in the continuous time. So this is actually not necessarily, this is not the classical AM. An AM would have a 1 plus cosine. That would be a classical AM. It's called double sideband suppressed carrier AM. And the reason that it is double sideband suppressed carrier is because you see two sidebands, hence the double sideband. And if you had a 1 over here, you would have also a delta function up here. And that is called a carrier. And so double sideband, two sideband. Suppressed carrier means no carrier, is this. Okay, so this is the spectrum of double sideband suppressed carrier. Okay. Now, why do you need to, why is that useful? Why is that? So if you have this 1, turns out that the receiver is really simple. It's really easy to implement a receiver. You can even take a 1 diode and basically like a headpiece and put them together and you can listen almost to this. It's really easy to demodulate. This one is a little bit harder to demodulate. And the reason is, if I send a cosine, if I modulate by a cosine, I need to demodulate by a cosine too. But what if I made a mistake and I demodulated by a phase shift? So if my transmitter and receiver are not exactly the same phase, and I demodulated by a sine. So I multiply by a sine. If I multiply by a sine to demodulate, sine and cosines are orthogonal, and I'll get 0 out. Okay? So that kind of modulation needs synchronized transmitter-receiver. Okay? Turns out that you can try to extract what the carrier is from this, but it doesn't matter so much. But this is kind of wasteful. The reason it's wasteful is because there's really only half the information. Like we're sending twice the signal that we need. We only need to send this. This is where the information is, right? We said that if I knew this, I can complete the other part because the signal is real. So why do I need to send now double the bandwidth? It's wasteful. You can filter it out. And if you filter it out, this is called single sideband. And that basically uses the exact fact of conjugate symmetry in order to save bandwidth. Okay? So now you're sending something that is more narrow. Okay, you remove this. And this is called single sideband. In this particular case, it's called upper sideband. Called upper sideband because it's the upper part. And guess what? What's the other side called? LSB. Yeah, LSB and USB. That's right. Great. Okay, so these actually are used heavily in amateur radio. And I'm going to give you an example. There's a website called WebSDR. WebSDR is like people have SDR, software-defined radios, in their home, connect it to antennas, digitize it, and there's a server. They're running servers that you can just tap into anywhere in the world. I mean, there's a lot of servers out there. I can show you a map. And great. And these are all these servers that in the world that you can now just listen to what they're picking up. And they're all being transmitted. But I want to go to a particular one. I really want to go to a particular one, which is this one. No, don't say that. Ah, great. Okay, let's pick one from the U.S., North America. And we'll pick something with a 20-meter band. And let's pick someone from here. That sounds good. What? Now, why is that? Fantastic. Let's try again, one more time. America. AirBears 2 is blocking it, but EduRoam forks. Okay. So I'm going to pick a particular frequency, which is on the 20-meter band. It's this one. And now you see a waterfall diagram. And let me just make it a little bit bigger. So you see here different signals. And the signal over here that you see I'm going to zoom in. It has a carrier. And it's actually amplitude modulation. Okay? This is some, I think, religious shortwave station. But you see the double bands, the double sidebands, and the carrier. It has a carrier. Okay? Now, if I move the demodulation a little bit off band, do you see a difference? It's pretty robust. So for that wasteful energy, I get some robustness to it. Now I'm going to use a less robust one. I'm going to look at the amateur radio band. And this one over here, that's great. See the difference? Because what the demodulator really is doing is trying to replicate that to create what will be a real signal. And if I don't demodulate right, I'm going to get this, kind of Donald Duck effect. Too high frequency. Too low frequency. Just right. Okay? All right, questions? So this is how. So now you traded off efficiency, but now the receiver has to be a little bit more complicated. You really need to know what the frequency is. Okay, does this make sense? Okay. WebSDR, I recommend looking at. It's a really nice place to look at the spectrum everywhere in the world. Okay. Other properties: time reversal. Time reversal. If you flip the sign on your end, so you flip your signal, you also have a negative in your Fourier transform. That's really nice. And if you remember that this is also, so if x is actually real, this is also equal to the conjugate. And if it also equals to the conjugate, so if something equals to its conjugate, that means that if a number is equal to its conjugate, what does it mean? It's real. That's right. So that means that the signal is real. So if this equals to the conjugate, that means that that the Fourier transform is going to be real. Hence, if you've got an even signal, so a signal that's even symmetric, okay, so it has a symmetry that's even, then its Fourier transform is going to be real. Okay, that's a private case. So now the question is, if I have x of n, and this is my Fourier transform, and I take the real value of that, what's going to happen? Happened to me a few times. I got some what's called K-space in MRI, and by mistake, we made it real. What would happen? What does the signal then have to have if the Fourier transform is real? It's going to be even symmetric, right? So you're going to have the even symmetry part of it. So what you can do is effectively decompose this into an even and an odd symmetric signal. If you do this decomposition, you'll see that the even one is basically just a signal plus its flipped version. The odd one is the signal minus its flipped version. Okay, so then you've got this signals, and the even plus the odd will result in a real Fourier transform and an imaginary Fourier transform. So the imaginary part corresponds to the odd, the real correspond to the even part. If I look at an MRI, this is an MRI of a brain. If I take the real part of just the real part of the Fourier transform, take an inverse Fourier transform, I get this. Basically, I get the signal, flipped version of it, and added. Okay? It's kind of strange. but yet mesmerizing. Okay? All right. Some other properties of the Fourier transform. If this is the Fourier transform, what if I shift in samples? Shift in samples, get a modulation. In fact, it's a periodic modulation. Sorry, it is. Okay, so it's a modulation because the signal is periodic. Then everything kind of wraps up. Okay, so any shift, you get a modulation. What about if you modulate in time or in samples? Then you got a shift. Okay. This is also great for MR. And the reason it's great for MR is sometimes because of system imperfections, you will have delays. So you're acquiring data in the frequency domain. You're thinking you acquire some part, but really your receiver is kind of delayed with what's going on. And all the Fourier transform is actually being shifted. So what happens is that instead of having the DC in the middle, like everything is shifted to the right. But the beauty about this, that it only modulates the image. So all that part of that shift only shows up in the phase. So if you look at the real part, or the magnitude doesn't change. It's only modulation. So the nice thing about this is this is robust to these kind of system imperfections. Okay? So if you look at the inverse Fourier transform, you see this is the magnitude and this is the phase. You see there's a linear phase. Something linear changes that way. Well, this is like nasty. Why is this nasty? Right. There's no phase is not defined when there's no magnitude. Okay. Phase is not defined when there's no. Only when there's magnitude you can define a phase. Right. Close to zero, like any small fluctuation will give you a random phase. Okay. That's exactly what you're saying. Phase is this amazing thing. Amazing. All right. We'll do one more example and then we'll finish. What is the DFT of this signal? Can you think of a way to use properties and to solve this? You can. I'm sure you can, but can you? What if you take the absolute value of this? Does it look like something we've seen before? Okay. Then how can we generate that?
So we're shifting our periodic sync by pi because we're multiplying.
That's the result, but how do you get that?
So we multiply our original box signal by e to the j pi n.
Nice. 12 points. 12 points. That's from the Eurovision. This is kind of like a European thing. It's the song contest that's in Europe, like a big hit. Cheesy songs for 3 minutes. Right. So modulating a rect will give you this, right? So effectively, this is this modulated by e to the j pi, and that shifts it by pi. So the whole thing shifts by pi. So now you took something that was a low-pass filter that was passing low frequencies into a high-pass filter that passes high frequencies. Okay? Any questions? We'll continue next time. Next time we'll continue with the DTFT and go through the Z transform, but we're not going to spend on the Z transform more than next lecture. So it's going to be very little. So read chapter 3 as well if you need to remind yourself about the Z transform. Questions before we go? I know you want to go, but let's have one question. It could be general. Talk to me. Converse. Yeah. Oh, now that's a great question. 532 Corey. Yeah. So it's a room that says printer and a ham shack. A copier room, and a ham shack. So it's like half the room is a copier, half the room is like radios, and then we have a nice cable that goes to the roof. By the way, if you ever walk a little bit further away from Corey, you'll see this like really gorgeous looking large antenna, vertical, with like three wires coming out of this, guy wires. This amazing antenna is ours. And it's a prominent feature of the Corey building now. Okay? It covers most of the bands on the shortwaves range, so HF. And we have a really nice, super expensive software-defined radios in the shack, which once you've got your license, you're welcome to use it by yourself, and before that, with somebody else. Yeah. All right. See you on Wednesday. There's discussion here right now. RTAs are like super good, super expert, and amazing. So you should listen to them. Oh, hi, John.